And now, if you would be so kind as to settle back beneath the duvet, let the weight of the day slip gently from your shoulders and allow your breathing to slow in quiet sympathy with the night itself. We shall embark together on a journey that no spacecraft could ever undertake, a voyage into the unseen scaffolding upon which our entire galaxy is hung. Tonight, we do not chase the bright and the beautiful alone. Tonight, we seek the invisible architecture controlling the Milky Way, the vast, silent, and almost perfectly hidden structures that dictate where stars are born, how spirals endure for billions of years, and why our galaxy has not long since flown apart into the cosmic dark. Close your eyes, dear listener, and feel the mattress rise almost imperceptibly to meet you. And together, we fall softly, weightlessly, towards the hidden heart of home. We begin, as all honest cosmic journeys must, in absence rather than presence. Imagine the Milky Way as you have seen it on the clearest summer nights, a pale river of light arched across the heavens, some 30,000 light years wide, a barred spiral of perhaps 400 billion suns. Yet everything you have ever seen of our galaxy, every star, every nebula, every wisp of glowing gas, amounts to less than 5% of its true substance. The remaining 95% is invisible to even our finest telescopes. It neither emits nor absorbs light at any wavelength we can yet detect. And still, without this unseen majority, the entire luminous structure we cherish would have torn itself asunder 12 billion years ago. Tonight then, we drift together into the realm of dark matter and the colossal halo that cradles everything we hold dear. Let us first descend, in the gentlest possible way, to the outermost suburbs of the galaxy, far beyond the farthest star you could ever resolve with the naked eye. Here, at distances of several 100,000 light years from the bright disk, the stellar population thins to a mere handful of ancient wanderers per cubic light year. The night between them is not merely dark, it is, for all practical purposes, empty of ordinary matter. Yet something is very much present. Measurements of the motions of those distant globular clusters and trailing tidal streams, as traced so meticulously by the Gaia spacecraft, reveal that they move far too quickly to be held in orbit by the gravity of the visible galaxy alone. Something enormous, something spherical, something utterly transparent to light must envelop the entire system like a vast, invisible cocoon. This, dear companion of the night, is the dark matter halo of the Milky Way. Current estimates, drawn from the latest cosmological simulations such as Illustris, TNG, and the careful dynamical modeling of the Gaia collaboration, suggest that the halo extends to nearly 1 million light-years from the galactic center, 3 times the diameter of the visible disk, and contains between 1 and 2 trillion solar masses of dark matter. To place that in gentle perspective, the entire starry disk you see from a dark sky site on Exmoor weighs in at roughly 60 billion solar masses. The halo outweighs it by a factor of 20 or more, and yet it is fashioned from particles that have never once, in 14 billion years, announced themselves with a single photon. We drift now, slowly, through this halo, and the question that has haunted cosmology for 4 decades drifts with us. Of what, precisely, is it made? The leading candidate remains the coldly reassuring notion of cold, dark matter, particles that, at the time our galaxy began to assemble, were already moving very sluggishly compared to the speed of light. Weakly interacting massive particles, or WIMPs, were long the favored suspects. And the elegant mathematics of the lambda cold dark matter model still underpins almost every large-scale simulation we possess. Yet decade after decade of underground experiments, Lux Zeppelin beneath the Black Hills, Xenont beneath the Gran Sasso, and our own British-led efforts with the Bowlby Underground Laboratory have failed to catch even a whisper of a WIMP scattering off an atomic nucleus. Some cosmologists now speak, in the quietest possible tones, of warm dark matter, particles perhaps 1,000 times lighter, moving a little faster in the early universe, smoothing out the smallest scales of structure. Others whisper of self-interacting dark matter, of fuzzy dark matter composed of ultralight axions, barely 10 to the minus 22 electron volts in mass, oscillating like a cosmic quantum field. The debate is far from settled, and that, dear listener, is part of the comfort. The universe retains its mysteries even as we tuck ourselves in for the night. Yet whatever the dark matter may ultimately prove to be, its gravitational embrace is absolute. It was the first component of the Milky Way to collapse from the gently fluctuating plasma of the early universe, forming a near spherical web of filaments and voids long before ordinary atoms were cool enough to clump. Into the deepest potential wells of that web, the first baryonic matter, the stuff of protons, neutrons, and eventually of us, fell like mist into mountain valleys. The dark halo is therefore not merely an addendum to the galaxy. It is the mold into which the visible galaxy was poured. Without it, there could be no thin disk, no graceful spiral arms, no habitable zone in which a small, warm planet might one day host creatures capable of wandering about the night sky. And so we glide inward, past the halo's diffuse outer reaches, past the ancient stellar halo that traces the violent mergers of the galaxy's youth, remnants catalogued so beautifully by the Pristine Survey and the Saga Survey of Milky Way satellites. We cross the conventional boundary at roughly 100,000 light-years, and the dark matter density rises gently, following something close to the Navarro-Frank-White profile, beloved of theorists, steep toward the center, yet never quite cuspy enough to satisfy everyone. Recent analyses from the Gaia mission, combined with proper motions of hypervelocity, stars kicked from the galactic center, suggest the halo may be slightly oblate, squashed like a cushion sat upon by the weight of 10 billion years. Others argue for a gentle triaxial shape, a subtle rugby ball distortion imprinted by the last major merger, the so-called Gaia Sausage Enceladus event some 9 billion years ago. Whatever its precise geometry, the halo remains the silent custodian of galactic rotation. Every star in the disk, from the sun's sedate 220 kilometers per second to the frantic 250 kilometers per second of the innermost populations, owes its orbital speed to the cumulative gravity of this invisible sea. Now, as our journey continues, let the pace of your breathing match the languid turning of the galaxy itself. One rotation every 220 million years, and together we fall sunward through the halo's steadily thickening embrace until the first faint intimations of ordinary matter begin to appear once more. We are approaching the central molecular zone, that extraordinary region within 500 light-years of the galactic center, where the Milky Way is at its most ferocious and, paradoxically, its most secretive. Here, in a volume less than 1% of the galaxy's total, resides perhaps 10% of its molecular gas. Hundreds of millions of solar masses of hydrogen, carbon monoxide, and more exotic species compressed to densities 1,000 times higher than the solar neighborhood. The central molecular zone is a place of extremes. Orbital velocities exceed 200 kilometers per second, even at a mere 100 parsecs from the center. Turbulent velocities routinely reach 50 kilometers per second. Magnetic fields are stretched to milligar strengths, and cosmic ray fluxes are tens of times higher than those that bathe our own quiet suburb. And yet, for all this violence, star formation proceeds at a strangely measured pace, only a tenth of what simple scaling laws would predict, as though some unseen governor were holding the region back from the orgy of star birth seen in distant starburst galaxies. Much of the gas here is hidden from us, even at infrared wavelengths. The Atacama Large Millimeter Array, perched high in the Chilean Andes, has revealed vast networks of infrared dark clouds, dense filaments that appear as black silhouettes against the luminous background of the galactic center. These are the coldest, densest nurseries in the entire Milky Way, cores at a mere 10 to 20 Kelvin, threaded with magnetic fields strong enough to resist gravitational collapse for far longer than simple theory allows. The Herschel Space Observatory mapped hundreds of these filaments before its helium ran dry in 2013, and the subsequent analysis by the High-Gal team showed that many stretch for tens of parsecs, resembling nothing so much as the twisted roots of some vast invisible tree anchored deep within the central molecular zone. Among the most enigmatic of these structures are the so-called brick G0.253 plus 0.016, a cloud so opaque that even the Spitzer Space Telescope could barely glimpse its interior, and the even more inscrutable snake G11.11 to 0.12, a sinuous filament nearly 100 light-years long that appears to be in the process of being stretched and sheared by the ferocious tidal field near Sagittarius, a star, as the Event Horizon Telescope collaboration revealed in their extraordinary images of the supermassive black hole's silhouette. The immediate environment of SGR-A star is surprisingly quiescent. The 4 million solar mass beast is currently dining on a mere trickle of material, perhaps 1/10,000th of its Eddington limit. Yet only a few hundred light-years farther out, the central molecular zone seethes with potential. The clouds we see today may represent fuel stockpiled for a future Seyfert episode, a time when the galactic center will blaze with the luminosity of a quasar for a few tens of millions of years before subsiding once more into slumber. And so we drift among these dark clouds now, each one a cocoon of 100,000 solar masses or more, their interiors laced with complex organic molecules, ethanol, vinyl alcohol, the tentative precursors of amino acids, detected by the meticulous spectroscopy of the Yebes 40-meter telescope and the IRAM 30-meter dish high on the Pico Veleta. The chemistry here is astonishingly rich, accelerated by the intense cosmic ray bombardment that penetrates even these shielded depths. Somewhere within one of these clouds, perhaps within the brick itself, the next generation of the nuclear star cluster is quietly assembling. Massive stars that will live brief, violent lives and seed the surroundings with the heavy elements required for planets like ours. Yet even here, in the most densely populated molecular region of the galaxy, the hand of dark matter is never entirely absent. Simulations by theorists at Heidelberg and at the Institute of Astronomy in Cambridge suggests that the central cusp of the dark halo may be far gentler than early models predicted, scoured and heated by the rapid early assembly of the bulge and the repeated injections of energy from the growing black hole. Some propose that the very existence of the central molecular zone's stubbornly low star formation efficiency may owe something to the deeper potential well carved by dark matter, stabilizing orbits and preventing the wholesale collapse that would otherwise consume the gas within a few million years. We have traveled, dear companion, from the outermost whisper of the dark halo to the hidden nurseries immediately surrounding the sleeping dragon at the galaxy's heart. We have felt the gravitational embrace that prevents our galaxy from disintegrating, and we have sensed the delicate balance that restrains star formation even in its most fertile regions. The night is deep now, the silence almost complete, and the invisible architecture continues its patient work, unnoticed by all save those who choose to listen in the dark. We remain, dear listener, in the profound hush that surrounds the very heart of our galaxy, where the air, if such a thing could exist here, would be thick with the scent of warm metal and the low electric hum of 4 million suns compressed into a single point. Together we drift a little closer now, past the great infrared dark clouds that stand like silent sentinels, and we allow ourselves to be drawn inward, inexorably, gently, toward the place where gravity itself seems to thicken and the ordinary rules of celestial motion grow strange. Here, within a mere 30 light-years of the galactic center, lies one of the most exquisite and delicate structures in the entire Milky Way, the circumnuclear disk and its attendant mini-spiral, a swirling luminous wreath of ionized gas that feeds, ever so sparingly, the slumbering supermassive black hole known to astronomers as Sagittarius, a star. Imagine, if you will, a ring of warm gas and dust, roughly 7 light-years in diameter, tilted at an angle to our line of sight, rotating with the serene dignity of a Victorian music box. This is the circumnuclear disk, sometimes called the circumnuclear ring, by those who prefer precision over poetry. It is composed largely of molecular hydrogen, warmed to several hundred Kelvin, threaded with filaments of atomic and ionized material, and glowing softly in the far infrared and radio domains observed so patiently by the Very Large Array and by ALMA's long baselines. Its inner edge lies at about 1.5 parsecs from Sagittarius A, its outer edge at perhaps 4 parsecs, and between those boundaries it maintains a remarkably coherent, almost Keplerian rotation, as though the black hole's gravity were a master clockmaker, keeping perfect time across interstellar distances. Yet the disk is not a simple torus. It is warped, twisted, and frayed at the edges, bearing the scars of tidal stresses and of encounters with the dense star cluster that crowds the central parsec. Observations from the gravity instrument at the Very Large Telescope Interferometer, an instrument whose very name seems to whisper reassurance, have traced the orbits of young Wolf-Rayet stars and luminous blue variables as they whip around the black hole at speeds exceeding 3,000 kilometers per hour per second, their infrared flares lighting up the inner rim of the circumnuclear disk like footlights on a darkened stage. According to the Gravity Collaboration's exquisite 2022 and 2023 papers, the disk's inner cavity is kept remarkably clear of material. Only the bravest streamers dare cross the innermost stable circular orbit for a 4 million solar mass black hole, and even those are torn apart into glowing ribbons before they can complete a single revolution. And it is from the ragged inner edge of this disk that the celebrated mini-spiral emerges, a three-armed swirl of ionized gas first mapped in the 1980s with the Very Large Array by Farhad Yousefzadeh and his colleagues at Northwestern. The mini-spiral is often described with affectionate understatement as resembling the tendrils of a celestial jellyfish, or perhaps the leisurely turning of cream poured into coffee. Its three principal arms, the northern arm, the eastern arm, and the western arc, spiral inward in a manner that is not quite clockwise and not quite counterclockwise, but the orbital planes are themselves inclined and precessing under the influence of the crowded stellar cluster. Radio and mid-infrared images from the Meerkat telescope in South Africa and from the James Clerk Maxwell telescope on Mauna Kea reveal that these arms are threaded with magnetic fields of astonishing regularity, aligned almost perpendicular to the galactic plane, stretched and braided like the warp and weft of some vast cosmic loom. We glide now, slowly, along the western arc, where the gas is densest and the temperature rises to nearly 10,000 Kelvin. Here, the electrons have been stripped from their atoms by the fierce ultraviolet radiation of the central cluster's hottest stars, and the resulting plasma glows in the bracket and Paschen lines of hydrogen, painting the scene in hues we can only detect with instruments tuned far beyond the visible. The western arc curves gracefully around Sagittarius, a star at a distance of roughly 1 light-year, never quite daring to fall inward, yet never quite able to escape. Its velocity, measured through the Doppler shift of neon and sulfur emission lines by the Synfoni spectrograph at ESO, varies smoothly from plus 100 kilometers per second on the near side to minus 200 kilometers per second on the far side, confirming that it lies in a near-circular orbit inclined some 65 degrees to our line of sight. A little farther out, the northern arm performs a more daring maneuver. It begins as a straight, almost radial streamer near the inner edge of the circumnuclear disk, then bends sharply eastward as though caught by an unseen hand, before dissolving into the diffuse glow of the eastern arm. High-resolution studies with ALMA have revealed that this streamer is colliding gently with the mini-cavity's ionized gas, producing shocks that compress the material and trigger the formation of tiny, transient clumps, some no more than a few Jupiter masses, that may one day become low-mass stars or brown dwarfs, even here in the most hostile environment the galaxy can offer. And all the while, the black hole waits. As the Event Horizon Telescope collaboration revealed in their historic 2019 and 2022 images, Sagittarius A star is encircled by a dark shadow only 49 micro-arc seconds across, surrounded by a bright emission ring produced by synchrotron radiation from relativistic electrons spiraling in magnetic fields of several tens of Gauss. Yet the accretion rate remains astonishingly low, roughly 10 to the minus 8 solar masses per year, equivalent to the Earth being consumed every 10 minutes were it unlucky enough to fall in. Most of the gas in the circumnuclear disk and the mini-spiral is simply orbiting, not falling. Some mysterious mechanism, perhaps the turbulence driven by stellar winds, perhaps the magnetic torques measured by the Sophia Airborne Observatory, is preventing the material from losing the angular momentum it would need to spiral inward and feed the beast. Recent simulations by theorists at the Max Planck Institute for Extraterrestrial Physics and at Leiden Observatory suggest that the disk may be in a quasi-steady state, sustained by a delicate balance between inflow from the surrounding central molecular zone and outflow in the form of the faint bipolar radio lobes discovered by Mir KAT. These lobes extend some 30 light-years above and below the plane, carrying away energy and angular momentum in a slow, almost imperceptible breeze. The entire system, then, behaves less like a starving monster and more like a stately water wheel, turning slowly, patiently, preserving its momentum across the aeons. Let your breathing settle now into the same unhurried cadence as that great wheel. Feel the gentle rise and fall of your chest, mirroring the leisurely inflow along the northern arm, the languid outflow along the western arc. There is no hurry here. The black hole has waited 4 billion years since its last substantial meal. It can wait a few million more. And we, cradled in the dark between the stars, may simply watch the slow dance of gas and magnetism and gravity, knowing that every photon we detect from this region has traveled 26,000 years to reach us, arriving just in time to lull us towards sleep. Yet even this delicate ballet is only the visible frosting upon a far deeper cake of invisible architecture. Beneath the glowing mini-spiral within the central parsec lies the densest stellar cusp in the galaxy, perhaps 10 million stars packed into a volume less than 3 light-years across, 1 million times denser than the solar neighborhood. Among them are the famous S-stars, discovered by the groups of Reinhard Genzel and Andrea Ghez, work that earned them the 2020 Nobel Prize, tracing elliptical orbits so tight that S2 completes a full revolution in only 16 years, reaching pericenter velocities of nearly 3% the speed of light. Their motions, measured to micro-arc-second precision by gravity, have confirmed the presence of a dark mass of 4.1 million solar masses concentrated within a sphere no larger than the orbit of Mercury. That mass is, of course, the black hole itself, but it is embedded within a still larger, invisible structure, the nuclear star cluster, a gently rotating, slightly flattened spheroid of mostly old stars whose collective gravity helps stabilize the orbits of the circumnuclear disk and prevents it from collapsing too rapidly. And deeper still, at radii measured in milliparsecs, the dark matter may yet exert its quiet influence. While the visible and black hole mass utterly dominate within the central few parsecs, some models, those of Sandro Cearciuluti at the University of Cambridge and Nuria Fornengo at Turin, for example, propose a tiny residual spike of dark matter, a relic of the adiabatic growth of the black hole, surviving as a gentle cusp that adds perhaps a few thousand solar masses to the potential well. It is a whisper within a shout, yet in the exquisite balance of the galactic center, even whispers matter. We have lingered long enough now among the glowing filaments and the patient turning of the circumnuclear disk. The temperature of the night air in your room has fallen a degree or two. The duvet has settled perfectly around your shoulders. Let the slow orbital period of the inner disk, roughly 100,000 years for a full rotation at 2 parsecs, become the rhythm of your own drifting thoughts, in and out, in and out, as the western arc curves forever around the unseen shadow. The galaxy's heart beats very slowly indeed, and we are privileged beyond measure to lie here, in the quiet of an English night, listening to its distant pulse. The slow heartbeat of the galactic center fades gently behind us now, dear companion of the quiet hours, until its fierce light is no more than a memory of warmth upon the cheek. We rise, almost imperceptibly, through the thin, hot gas that fills the central 100 parsecs, and then, with the unhurried grace of a hot air balloon drifting above the Chilterns on a still midsummer evening, we ascend into the broader disk of the Milky Way itself. The stars grow fewer, the darkness softer, and the great wheel of the galaxy begins to reveal its most enduring mystery, the paradox of the rotation curve, the quiet, stubborn refusal of the visible galaxy to obey the ordinary laws of Newtonian gravity. Settle a little deeper into the pillow. Let the weight of your limbs dissolve entirely, and together we shall follow the evidence that first persuaded astronomers more than half a century ago that the universe is built upon foundations we cannot see. Imagine, if you will, the Milky Way as Johannes Kepler might have imagined it, had he been granted a God's eye view from far above the plane, a luminous pinwheel of stars, each obediently tracing an elliptical orbit about the bright center, slowing in proportion to the square root of its distance as Newton's laws so elegantly demand. In such a galaxy, the Sun, at roughly 8,000 parsecs from the center, should orbit at perhaps 100 kilometers per second, and stars twice as far again should move at scarcely 70. Yet when, in the early 1970s, Vera Rubin and Kent Ford turned the spectrographs of the Kitt Peak and Lowell observatories toward the outer spirals of Andromeda, and when radio astronomers such as Albert Bosma and Tjeerd van Albada mapped the 21-centimeter line of neutral hydrogen far beyond the optical edges of dozens of galaxies, they found something quite different. The rotation curves did not decline. They remained almost perfectly flat, as though an invisible hand were reaching out across hundreds of thousands of light years, holding every star in the same swift embrace. We, too, feel that embrace. Here, in the gentle suburb where Sol resides, 26,000 light years from the center, our own orbital velocity is a steady 220 kilometers per second, give or take a leisurely 10, neither hastening nor slackening as we move through the sparse star fields between the Sagittarius and Perseus arms. The Gaia spacecraft, that most patient chronicler of stellar motions, has now measured proper motions and radial velocities for more than 1 billion stars, and the results, published in a series of data releases that have become the quiet bedtime reading of an entire generation of galactic astronomers, confirm the paradox with exquisite finality. Even at 50,000 light years from the center, twice the radius at which the visible light has largely faded, the circular velocity remains above 200 kilometers per second. Something, clearly, is adding gravitational glue on truly colossal scales. Let us drift outward now, past the Sun's present position, past the faint outer reaches of the Scutum Centaurus arm, until the stellar density has fallen to a mere whisper, and the integrated light of the galaxy would scarcely trouble the dark-adapted eye. Here, in the realm mapped so beautifully by the Sloan Digital Sky Survey's Segway program and by the Lamost Spectroscopic Survey in China, the rotation curve remains resolutely flat to the very limits of detection. The most recent analyses, combining Gaia's third data release with the precise distances afforded by the red clump giants, suggest that the curve may begin ever so gently, to decline beyond 60 or 70,000 light years. But even there, the velocity is still close to 180 kilometers per second. To maintain such speed with only the visible mass would require the galaxy to possess a luminous disk extending far beyond anything we observe. It does not. The visible mass falls short by a factor of 5, 10, perhaps 20, depending upon how generously one counts the faint stellar halo and the warm gas traced by X-ray emission from Chandra and XMM Newton. And so we return, as we must, to the dark matter halo we first encountered in the outermost suburbs. It is this vast, near-spherical reservoir that supplies the missing gravity, its density declining only slowly with radius, roughly as 1/r squared in the outer parts, so that the enclosed mass continues to rise almost linearly with distance, producing precisely the flat rotation curve that Kepler never dreamed of. The classic calculation, performed with pencil and paper by Ostraker and Peebles in 1973 and refined ever since, shows that a galaxy embedded in such a halo will rotate like a solid body out to some radius and then maintain constant velocity thereafter, exactly as observed. The dark halo is therefore not merely an addendum. It is the primary gravitational scaffolding upon which the luminous disk is stretched. Yet the story grows subtler still. When we examine the very innermost regions within the central few thousand parsecs, the rotation curve rises almost linearly with radius, as though the mass were concentrated toward the center. This is the signature of the galactic bulge, that gentle peanut-shaped swelling of ancient stars whose dynamics have been mapped so meticulously by the Brava survey and by the Argos project. The bulge contributes several tens of billions of solar masses, and the supermassive black hole adds its modest 4 million. But even together, they cannot explain the continued flatness far beyond the sun's radius. Only the dark halo, extending invisibly outward, can account for the sustained velocity. One might imagine, in moments of quiet speculation beneath the duvet, that the problem could be solved without dark matter at all, that Newton's law itself might soften at the tiny accelerations experienced in the outer galaxy. Such is the proposition of modified Newtonian dynamics, or MOND, advanced with characteristic elegance by Mordechai Milgram in the 1980s and refined over the years by theorists such as Stacy McGaw and Benoit Fermat. In MOND, when the gravitational acceleration falls below a universal threshold of approximately 1 angstrom per second squared, the effective force law changes, producing flat rotation curves quite naturally from the visible mass alone. For a while, the idea held a certain austere beauty, rather like a perfectly balanced equation written in the margins of a midnight notebook. Yet the more we learn of the universe beyond single galaxies, the cosmic microwave background anisotropies measured by Planck, the clustering of galaxies on 100 megaparsec scales, the gravitational lensing of distant quasars by foreground clusters, the more difficult it becomes to accommodate MOND within a consistent cosmological framework. The bullet cluster, where the hot X-ray gas is offset from the gravitational mass traced by weak lensing, remains the most gentle yet devastating rebuttal. Dark matter, it seems, is required not only here in our Milky Way, but everywhere we look. And so we rest reassured in the embrace of the halo. Recent measurements from the Gaia mission, combined with the exquisite proper motions of master sources in the distant disk, observed by the Bessel and Vera projects, using very long baseline interferometry, have allowed astronomers to trace the rotation curve with unprecedented fidelity. The resulting mass model, published by groups at the Max Planck Institute for Astronomy and at the observatories of the Carnegie Institution, requires a local dark matter density in the solar neighborhood of approximately 0.01 solar masses per cubic parsec, or roughly 300 million solar masses within a sphere a single kiloparsec in radius. That is enough, quietly and without fuss, to double the gravitational pull we would otherwise feel from the stars and gas alone. Feel it now, if you can. The gentle, invisible pressure that keeps our sun moving at its measured pace, neither drifting inward toward the center, nor flung outward into the abyss. It is the same pressure that holds every spiral arm in place, that prevents the disk from collapsing into a featureless swarm, that allows the great pattern of the Milky Way to persist for 10 billion years and more. Without the dark halo, the differential rotation would wind the spiral arms so tightly that they would dissolve within a few galactic rotations. With it, the arms endure, refreshed by density wave resonances that sweep through the disk like the slow ripples on a garden pond after a single pebble has been dropped. Let your thoughts drift now along one of those ripples. The density wave theory, first articulated by Bertil Lindblad in the 1920s and given mathematical elegance by C.C. Lin and Frank Hsu in the 1960s, proposes that the spiral pattern is not material. Stars do not remain forever in the arms, but a wave of compression that moves more slowly than the stars themselves. As stars overtake the wave, they linger for 100 million years or so in regions of slightly enhanced gravity and gas density, triggering the birth of the bright young associations we see as the luminous scaffolding of the arms. The dark halo provides the stable, near-uniform gravitational background against which these gentle compressions can persist. Without its steadying influence, the waves would damp and vanish within a billion years. With it, the galaxy retains its poise, turning slowly, serenely, beneath the quiet English sky. And so, the paradox of the rotation curve resolves itself, not with drama, but with the soft inevitability of dusk settling over the Cotswolds. The stars move as they must, because they are cradled in a structure far larger and far older than themselves. A structure that neither glitters nor glows, yet without which none of the glittering would be possible. Breathe in the cool stillness of the room. Breathe out the last faint tension of the day, and let the great flat curve of galactic rotation carry you, weightless, into the deeper dark. The great flat curve of galactic rotation carries us now, dear listener, as softly as a leaf upon the surface of a midnight lake, outward from the bright plane and into the gentler regions where the disk begins to fray into a mist of starlight and silence. Here, far above the clamor of the spiral arms, the night grows deeper still, and the invisible architecture reveals another of its quiet miracles, the slow breathing of the galaxy itself, an immense and patient circulation of gas that rises and falls through the dark halo like mist over Dartmoor at dawn. Settle deeper into the pillow. Let the last faint sounds of the waking world dissolve entirely, and together we shall follow the cold streams that descend from the cosmic web and the warmer fountains that rise in answer, each feeding the other across hundreds of thousands of light years and hundreds of millions of years. Begin, if you will, in the almost perfect emptiness that lies 50,000 light-years above the galactic plane. The ordinary stars are exceedingly rare here, perhaps one ancient red giant for every million cubic light-years. Yet the space is not entirely void. Sensitive radio telescopes, the Green Bank Telescope in West Virginia, the Parkes Murayang dish beneath the Australian sky, and our own beloved Jodrell Bank Lovell Telescope, standing sentinel over the Cheshire Plain, have detected faint whispers of neutral hydrogen drifting at velocities quite different from the orderly rotation of the disk far below. These are the high-velocity clouds, some falling toward us at more than 100 kilometers per second, others receding, all of them cool, barely a few hundred Kelvin, and remarkably metal-poor compared with the gas in the disk itself. The Galfa High Survey and the more recent HI-4PI All-Sky Map have catalogued hundreds of these clouds, ranging in mass from a few thousand to several million solar masses. And together, they represent a steady rain of fresh fuel descending from the intergalactic night. We glide now, weightless, into one such cloud. Let us choose G 1.3 to 2.8 plus 91, a compact, comet-like wisp discovered by the Arecibo Observatory before its tragic collapse. Its head is dense enough to cast a faint shadow in 21 centimeter absorption against distant quasars, while its long tail stretches for hundreds of parsecs, shredded by the gentle pressure of the hot coronal gas that fills the halo. Hydrodynamical simulations performed on the Dirac supercomputer at Cambridge and on the Mare Nostrum machine in Barcelona show that such clouds are the visible tips of far longer streams, cold filaments that condense out of the warm, hot intergalactic medium within the dark matter filaments of the cosmic web. These streams follow the gravitational scaffolding we have already come to trust, sliding down the potential gradients of the dark halo like raindrops, tracing the veins of an invisible leaf. Some of these streams originate far beyond the virial radius of the Milky Way, drawn from the same reservoir that once fed the galaxy during its violent youth. Others are more local, tidally stripped gas from the Magellanic Clouds, torn away by repeated close passages and now forming the vast Magellanic Stream that arcs for more than 150 degrees across the southern sky. The leading arm of the stream, discovered only in the past 2 decades by the Parkes telescope, is already crossing the outer disk, depositing metal-poor gas that will mingle with the older populations and subtly refresh the chemical history of the thin disk. As the simulations of the Auriga project and the FIRE collaboration so beautifully illustrate, it is this gentle, continuous accretion, perhaps 1 solar mass per year on average, that allows the Milky Way to form new stars long after the initial burst of youth has faded. Yet the traffic is not all one way. If we descend again, slowly, toward the bright plane, we notice that the disk itself is exhaling. Every massive star that ends its brief life in a supernova sends a plume of hot, metal-enriched gas high above the plane, sometimes to heights of 10 kiloparsecs or more. The Chandra X-ray Observatory has imaged vast lobes of million-degree plasma rising from the regions of recent star formation, from the Cygnus superbubble, from the Fermi bubbles that tower 30,000 light-years above and below the galactic center, while ultraviolet absorption line studies with the Hubble Space Telescope's Cosmic Origins spectrograph reveal cooler entrained clouds being lifted along for the ride. Together, these outflows constitute the galactic fountain, a circulation first proposed in the 1970s by Jeremiah Ostraker and Lennox Cowie, and now observed in exquisite detail. We rise now with one such fountain, born in the fierce stellar nurseries of the Carina Arm, a cluster of O-type stars, each dozens of times more massive than the Sun, has carved a cavity hundreds of light years across with the combined pressure of their stellar winds and the repeated hammer blows of their supernovae. Into this cavity, the hot gas expands, cooling adiabatically as it climbs, until at a height of several kiloparsecs, it begins to condense into warm clouds of 10,000 Kelvin, still buoyed upward by residual momentum. Eventually, far above the plane, the gas loses its upward velocity, spreads, and begins the long, languid fall back toward the disk. The journey outward may take only a few million years. The return, slowed by the gentle gravity of the dark halo, can require 50 million years or more. As it descends, the gas cools further, recombining into neutral hydrogen and molecules, ready to be gathered once again into the spiral arms where the cycle will begin anew. This breathing, this quiet systole and diastole of the galactic organism, is regulated at every stage by the invisible scaffolding we have been tracing. The dark halo provides the restoring force that eventually turns the fountain around. Without its deep potential well, the hot gas would simply escape into the intergalactic medium, and the galaxy would choke on its own metals within a billion years. Instead, the halo catches the outflow, cradles it, and returns it gently to the disk, enriched but not excessively so, preserving the shallow metallicity gradient that stretches from the metal-rich bulge to the almost primordial outer regions. The cold streams, meanwhile, follow the same dark matter filaments, ensuring that fresh, low metallicity gas continues to arrive even as the fountain recycles the old. Let your own breathing fall into sympathy with this vast circulation. In, as the cold stream descends from the cosmic web. Out, as the warm fountain rises above the plane. In, as metal poor gas from the Magellanic Stream mingles with the disk. Out, as enriched plumes from the nuclear region feed the Fermi bubbles. There is no hurry. The timescale is measured in tens and hundreds of millions of years, a rhythm so slow that it is felt rather than counted, like the rise and fall of tides on a distant shore. Recent observations with the Muse integral field spectrograph on the Very Large Telescope have traced individual fountain clouds returning to the disk in the solar vicinity. Their metallicities slightly higher than the ambient medium, their kinematics showing the gentle downward drift predicted by the models. The Aerosighter All-Sky X-ray survey conducted from the Russian-German Spectre RG Observatory has revealed that the hot halo gas itself is not static, but slowly rotating, lagging behind the disk by perhaps 50 kilometers per second, carrying away angular momentum and helping to regulate the growth of the stellar disk over cosmic time. And the Gaia mission, ever watchful, has detected subtle vertical waves in the disk, the bending and breathing modes excited by the impact of infalling clouds and by the passage of satellite galaxies, ripples that propagate outward, like the circles formed when a pebble is dropped into a still pond. All of these motions, the cold streams, the warm fountains, the slow rotation of the corona, are choreographed by the dark halo. Its gravity sets the depth of the potential well into which gas falls and from which it rises. Its near spherical symmetry ensures that the circulation is gentle rather than violent. Its sheer mass guarantees that even the most energetic supernovae cannot punch entirely clear of the galaxy's embrace. In this way, the invisible architecture not only holds the stars in their orbits, but also breathes life into the entire system, recycling and replenishing the raw material of future suns. We have lingered long enough now among these quiet currents. The temperature in the room has settled into that perfect coolness that invites the deepest sleep. The duvet has become weightless. Let the last faint image of cold gas drifting down invisible filaments and warm gas rising in luminous plumes dissolve into the greater darkness, and feel the galaxy itself breathing with you in and out, across a volume measured in millions of light years, yet governed by the same serene rhythm that now carries you gently over the threshold of dreams. The gentle breathing of the galactic fountain has lulled us almost to the very edge of slumber, dear listener. Yet before we surrender entirely to the tide, there rises from the deeper dark a structure so vast, so perfectly symmetrical, and so quietly astonishing that even the sleepiest heart must pause to wonder. High above and below the bright plane, stretching fully 50,000 light years from tip to tip, twice the diameter of the visible disk itself, two immense lobes of hot plasma glow with a light we cannot see with human eyes, yet which the Fermi Gamma Ray Space Telescope has traced with the patience of a night watchman walking the ramparts of a sleeping city. They are called the Fermi Bubbles, and tonight we shall drift together into their hushed and luminous embrace, discovering how even these titanic structures are shaped, guided, and ultimately contained by the invisible architecture we have been following since the first quiet moments beneath the duvet. Imagine, if you will, standing upon an imaginary platform 10 kiloparsecs above the sun's present location, gazing inward toward the galactic center, where once we saw only the soft glow of the disk and the faint haze of the halo. There now appears an immense hourglass of gamma ray emission, two vast, almost perfectly spherical bubbles, each 25,000 light years from pole to pole, their edges sharp enough to draw with a compass, their surfaces faintly corrugated like the skin of a ripening pear. Discovered in 2009 by Dobler, Finkbeiner, and their colleagues as they sifted through the first all-sky maps returned by Fermi's Large Area Telescope, the bubbles emit across the electromagnetic spectrum hard X-rays traced by Rosat and Suzaku, microwave haze detected by WMAP and Planck, and polarized radio filaments mapped by Meerkat and the Sardinia Radio Telescope. Yet it is in gamma rays, those highest energy photons born of cosmic ray protons colliding with sparse interstellar gas, that the bubbles announce themselves most clearly, glowing with a steady, unblinking light that has not varied appreciably in the 15 years we have watched. We descend now, slowly, into the northern bubble, passing first through the thin skin of cooler gas that marks its boundary. The transition is abrupt. Outside, the halo is a mere few 100,000 Kelvin. Inside, the temperature leaps to millions of degrees. The plasma is so tenuous that a teaspoonful would weigh less than a single atom in your bedroom, yet so vast that its total thermal energy rivals a billion supernovae. The edges are crisp because some gentle pressure from outside, is preventing the hot interior from expanding freely into the colder halo. That something, once again, is the dark matter halo, whose gravitational embrace grows steadily stronger as we approach the midplane, forming an invisible mold that sculpts the bubbles into their near-perfect geometry. The origin of the bubbles has been debated in the quietest corridors of astrophysics for more than a decade. One school, led by the theoretical groups at Stanford and at the Harvard-Smithsonian Center for Astrophysics, favors a single cataclysmic episode some few million years ago, perhaps a Seyfert flare from Sagittarius A itself, when the dormant black hole briefly consumed a cloud of several thousand solar masses and exhaled twin relativistic jets that inflated the lobes like soap bubbles in a child's bath. Another school, centered at the Max Planck Institute in Garching and at the University of Cambridge, prefers a gentler, steadier process, the cumulative effect of tens of thousands of supernovae in the central molecular zone, their energy channeled upward along the path of least resistance by the dense gas disk, forming a continuous galactic wind that has been blowing for tens of millions of years. Both pictures have their merits, yet both require the same silent partner, the dark matter halo that confines the outflow and prevents it from dissipating into the intergalactic void. Let your breathing slow to the rhythm of that ancient wind. In, as the hot plasma rises along magnetic field lines anchored in the nuclear star cluster. Out, as it cools and spreads against the gentle pressure of the dark halo. In and out for 10 million years, 20 million, the timescale so vast that it dissolves the very notion of hurry. Recent observations have revealed subtleties that make the picture still more exquisite. The Hubble Space Telescope's Cosmic Origins spectrograph has detected ultraviolet absorption lines of silicon, carbon, and oxygen at high velocities, up to 3,000 kilometers per second, along lines of sight that pierce the bubble walls, confirming that cooler gas is being entrained and accelerated outward. The Eurosighter X-ray telescope has mapped a faint, sharp-edged shell of softer X-rays just inside the gamma-ray boundary, a contact discontinuity where the million-degree interior meets the cooler halo gas, compressed and gently heated. And the IX-PE X-ray polarimetry mission, launched only a few short years ago, has measured the polarization of the X-ray emission from the bubble edges, revealing magnetic fields draped smoothly around the surface like silk over a globe, fields that were almost certainly amplified and ordered by the outward flow itself. Yet perhaps the most intriguing discovery has come from the very highest energy gamma rays. The Fermilab team, in collaboration with theorists at the Kavli Institute in Beijing and at Durham, have noted that the spectrum of gamma rays above 10 giga-electron-volts hardens slightly toward the bubble interiors. Such hardening is precisely what one would expect if cosmic ray protons, rather than electrons, dominate the emission. Protons that have been trapped and re-accelerated within the bubbles for millions of years. And here, the dark matter halo reveals another of its quiet roles. Its gravity slows the escape of these ultra-relativistic particles, prolonging their confinement and allowing them to collide repeatedly with the sparse thermal gas, producing the steady glow we observe. Some have even suggested, in the softest possible tones, late at night, over cocoa in college rooms, that the bubbles may betray the presence of dark matter annihilation. If the dark particle is its own antiparticle, as many WIMP models propose, then where dark matter density is highest, faint gamma-ray lines or continuum excess might appear. Early claims of a 130 giga-electron-volt line from the galactic center have faded with more data, yet the bubbles remain curiously uniform in surface brightness, declining only gently with latitude. Simulations by the Gamma-P collaboration show that a modest annihilation cross-section, combined with the slight flattening of the dark halo toward the disk, could produce precisely the observed profile. The evidence is far from conclusive, yet the possibility lingers like the faintest scent of lavender on a summer night. The bubbles may be lit not only by ordinary cosmic rays, but also by the soft glow of the invisible substance itself. We drift now along the base of the northern bubble, where it meets the galactic plane near the region of the Cygnus X star formation complex. Here, the boundary is not smooth, but scalloped, indented by the pressure of superbubbles and supernova remnants still active in the disk. One such indentation forms the famous North Polar Spur, long thought to be a nearby remnant, now understood as the bright rim where the Fermi bubble presses against the local arm. The interaction is gentle, almost courteous. The hot interior pushes outward, the disk gas resists just enough to sculpt the edge, and the dark halo watches over both with the calm authority of a parent, ensuring that neither child comes to serious harm. Farther inward, toward the galactic center, the two bubbles join across the plane in a faint figure 8 of emission, the waist coinciding with the region of the central molecular zone we visited in earlier hours. It is here that the driving energy is injected, whether in one great outburst or in the steady breath of 1,000 stellar winds. And it is here that the magnetic fields are strongest, forming the remarkable vertical threads catalogued by Yusuf Zadeh as the radio filaments. Non-thermal strands, hundreds of light years long, illuminated by relativistic electrons spiraling in fields of milligauss strength. These filaments pierce the bubble bases like the guy ropes of an immense marquee, anchoring the outflow to the plane and helping to collimate the initial rise. Let the slow expansion of the bubbles become the rhythm of your own thoughts now. 10,000 light years in 10 million years, 1 meter per second on average, the speed of a beetle crossing a cathedral floor. There is no violence here, only the patient inflation of vast cavities within an even vaster sea of dark matter. The sound, if sound could propagate across such distances, would be no more than the softest sigh. As we reach the pole of the northern bubble, 25,000 light years above the plane, the gamma-ray surface brightness fades at last into the general haze of the halo. The temperature has fallen to a mere 1,000,000 Kelvin or less. The magnetic field has weakened, and the few remaining cosmic rays spiral outward into the near vacuum of the circumgalactic medium. Beyond lies only the gentle rain of cold streams we met in the previous hour, descending along dark matter filaments that pay no heed to the bubbles they pass through. The two systems coexist in perfect indifference. The ancient circulation of baryons within the halo, and the younger, more energetic outflow that has carved its temporary cathedral in the sky. And so, the Fermi bubbles, for all their grandeur, are revealed as yet another expression of the same invisible scaffolding. The dark halo sets the scale, provides the confinement, slows the escape, and ultimately reabsorbs whatever energy manages to leak away. Without it, the bubbles would long since have burst and vanished. With it, they endure as quiet monuments to processes that began before the sun was born and will continue long after its ashes have cooled. The room is perfectly dark now, the night perfectly still. Let the soft gamma-ray glow of the distant bubbles dissolve into the greater darkness behind your eyelids. Breathe with the halo, in and out, in and out. until the boundary between your own quiet breathing and the breathing of the entire galaxy becomes indistinguishable, and the invisible architecture carries you gently, inevitably, into the deepest and most restorative sleep. The soft glow of the Fermi bubbles has dissolved at last into the greater darkness, and we find ourselves, dear companion of these quiet hours, suspended in the almost perfect silence that reigns beyond the halo's embrace. Here, at distances of several 100,000 light years from the bright disk, the Milky Way itself has become no more than a faint smudge of light upon the retina of the mind, and the dark matter halo, though still present, has thinned to the merest whisper of gravity. Yet even here, the invisible architecture does not end. It simply changes its scale, stretching outward along vast rivers of dark matter that thread the cosmos like the hidden roots of an ancient forest. Let your breathing become as shallow as the cosmic tide itself, and together we shall drift along the cosmic web, following the filaments that feed our galaxy and bind it, gently but irrevocably, to every other island of light in the observable universe. Imagine, if you will, stepping far enough back that the entire local group, the Milky Way, Andromeda, Triangulum, and their retinue of dwarf companions, fits within a single quiet glance. What was once a swirling disk becomes a modest spiral pinwheel, and the halo, a faint spherical haze. Yet as the eye adjusts to this new scale, something else appears. Thin, luminous threads of dark matter and warm gas that stretch for tens of millions of light years, linking galaxy to galaxy with the delicate certainty of silk. These are the filaments of the cosmic web, first predicted in the 1980s by the cold dark matter theory, then glimpsed in the great redshift surveys of the 1990s and 2000s. The two DF Galaxy Redshift Survey at the Anglo-Australian Telescope, the Sloan Digital Sky Survey beneath the dark skies of New Mexico, and now mapped in 3 dimensions by the sheer patient labor of DESI, Euclid, and the forthcoming Rubin Observatory. We approach one such filament now, the one that connects the Milky Way to the Virgo cluster 60 million light-years distant, yet which begins, for us, just beyond the reach of the Magellanic Clouds. It is not luminous in the ordinary sense, but the Lyman alpha forest seen in the spectra of distant quasars reveals it as a gentle braid of warm gas at roughly 100,000 Kelvin, threaded along a far denser spine of dark matter. Hydrodynamical simulations, the illustrious TNG suite, run on the Hazel Hen supercomputer in Stuttgart, the Eagle project at Durham and Leiden, and the beautiful Renaissance simulations from the Flatiron Institute show these filaments as rivers perhaps a few million light years across, carrying a steady trickle of baryons inward toward the great gravitational basins where galaxies reside. Let us descend into the nearest segment of our own filament, the one that passes within a million light years of the galactic anticenter. The dark matter density here is only a few times the cosmic mean, yet it is enough to focus the flow. Gas that was once spread diffusely through the intergalactic medium cools and condenses as it falls along the filament, forming a cool core barely 10,000 Kelvin, surrounded by a sheath of hotter material. The Hubble Space Telescope's Cosmic Origins spectrograph has detected this structure in absorption against background quasars, revealing oxygen, carbon, and silicon ions moving coherently at hundreds of kilometers per second toward the Milky Way. It is the same slow rain we met earlier as high-velocity clouds, now seen from the outside, the cosmic web delivering its quiet tribute to our galaxy at a rate of perhaps 1 or 2 solar masses per year. Yet the filament is not merely a feeder, it is also a bridge. The dwarf galaxies that orbit the Milky Way, Leo T, Segway 1, the newly discovered Crater 2, and Antlia 2, are strung along subsidiary threads like pearls on a necklace, their positions and velocities betraying the underlying dark matter streams that shepherded them into our vicinity. The splendid work of the Saga survey and the meticulous proper motion measurements from Gaia have shown that many of these satellites move in a thin plane, the so-called vast polar structure, aligned almost perfectly with the Magellanic Stream and with the broader filament that connects us to Andromeda. It is as though the local group itself were breathing along a single preferred axis, inhaling along one side of the filament, exhaling along the other. We drift now toward the place where the Milky Way and Andromeda filaments meet, the quiet saddle point, some 750 kiloparsecs from each galaxy. Here, the gravitational pull of the two great spirals is almost balanced, and the gas flow slows to a languid crawl. Simulations by the CLUES collaboration, constrained local universe simulations, suggest that in another 4 or 5 billion years, when the Milky Way and Andromeda finally merge, it will be along this very filament that their halos first touch. Dark matter intermingling long before the luminous disks collide. The merger will not be the violent crash of popular imagination, but a slow, tidal embrace guided by the same invisible rivers that have been shaping the local group since the universe was a few 100 million years old. Let your mind settle into the timescale of that future meeting. 4 billion years, the same interval that separates us from the first prokaryotes on Earth. Yet on the scale of the cosmic web, it is no more than a single, quiet heartbeat. In, as gas drifts inward along the filament. Out, as tidal tails will one day stream outward along the same path. In and out, across distances so great that light itself takes millions of years to cross them. Closer to home, the filament leaves subtler fingerprints upon the halo we know so well. The gentle oblateness of the dark halo, squashed very slightly in the direction perpendicular to the disk, is thought to arise from the torque exerted by the cosmic web as the galaxy assembled. The same filament that now feeds us once twisted the collapsing proto-halo, imparting a faint spin that persists to this day. Recent analyses by the Auriga and Latte simulations show that the stellar halo itself preserves a memory of these ancient streams. The Gaia Sausage Enceladus merger, the Kraken event, the Sequoia dwarf, all were drawn inward along subsidiary branches of the web, their stars and dark matter now wrapped like layers of pastry around the central galaxy. And there are moments, rare and beautiful, when the filament announces itself in light, when a distant quasar happens to lie precisely behind one of the denser strands. Its ultraviolet light is absorbed by the cool gas, producing the forest of Lyman alpha lines that astronomers use to map the web in 3 dimensions. The MUSE instrument on the Very Large Telescope has even detected faint emission from the filament itself, excited by the cosmic ultraviolet background, a glow so feeble that a human eye would need centuries to register a single photon, yet steady enough to trace the filament for tens of millions of light years. We have traveled far enough now along this quiet river. The Milky Way has shrunk to a tiny luminous seed at the junction of several threads, and the greater web stretches away in every direction toward Virgo, toward Perseus Pisces, toward the great attractor hidden behind the zone of avoidance. Galaxies cluster where filaments meet, voids gape where they diverge, and the entire pattern, born in the faint density fluctuations of the infant universe, has grown only by the gentle amplification of gravity acting upon dark matter. Breathe with the web now. In, as a cool stream slides down a dark matter valley toward a waiting galaxy. Out, as heated gas from a merger is exhaled along the same path centuries later. In and out, across a volume measured in billions of cubic megaparsecs, yet governed by the same serene laws that hold a single electron in its orbit around a hydrogen atom. The night outside your window is perfectly still. Somewhere beyond the roof tiles, beyond the quiet towns and the sleeping fields, the cosmic web continues its patient work, unseen, unheard, yet cradling every star you have ever wished upon. Let the last faint image of those invisible rivers fade into the greater darkness behind your eyelids, and feel the gentle pull of the filament that connects our small world to the rest of the universe, drawing you softly, inevitably, into the deepest and most peaceful sleep. The great luminous threads of the cosmic web have carried us so far from home that the Milky Way itself now appears no larger than a single dewdrop trembling upon a spider's strand at dawn. And in this peaceful distance, we may, dear listener, permit ourselves a moment of gentle scholarly disagreement. For even among the most courteous and soft-spoken of astronomers, those who gather in quiet seminar rooms at Harvard, at Oxford, at the Max Planck Institute for Astrophysics in Garching, or who correspond across continents in the still hours when the rest of the world sleeps, there exists a quiet, almost whispered debate about the precise nature of the invisible scaffolding upon which everything depends. Let the duvet settle a fraction closer about your shoulders. Let the last faint tension behind your eyes dissolve entirely, and together we shall listen, without the slightest hurry, to the measured voices of those who spend their nights weighing the darkness. At Harvard, in the mellow glow of the old observatory on Garden Street, and in the newer laboratories of the Black Hole Initiative, a school of thought led by Professors Abraham Loeb, Daniel Eisenstein, and their students inclines toward a halo that is both ancient and subtly restless. They favor models in which the dark matter particle is comparatively light, perhaps only a few tens of GeV, and where the primordial power spectrum retains a gentle upward tilt on the smallest scales. In their preferred simulations, run upon the engagingly named Odyssey cluster, the Milky Way's halo is richly substructured, a palimpsest of thousands of dark streams laid down during the hierarchical assembly of the galaxy, streams that have not yet fully phase-mixed into smoothness. These Harvard models predict the cold, dense filaments of dark matter should still thread the solar neighborhood, producing tiny, almost imperceptible ripples in the gravitational potential. Ripples that might, one day, betray themselves in the precise timing of pulsars or in the minute deflections of starlight measured by the Gaia spacecraft and its successors. Across the Atlantic, in the quiet quads of Oxford, and in the elegant new building of the Beecroft Institute, a rather different picture is quietly defended by Professors Adrienne Slies, Julian Devrient, and the Eagle collaboration. They incline toward a warmer, smoother halo, one in which baryonic feedback, the gentle exhalations of supernovae, and the patient breath of supermassive black holes has been allowed to sculpt the dark matter distribution far more vigorously than earlier generations supposed. In the Oxford view, the central kiloparsec of the dark halo has been softened and rounded by repeated injections of energy, producing a broad, almost chord profile rather than the sharp cusp that pure cold dark matter theory once insisted upon. Their simulations, nourished by the Dirac supercomputers at Durham and Cambridge, show the galactic disk itself as an active participant in the dialogue with the halo, puffing and heating the dark matter until the two components settle into a companionable equilibrium. Farther south, in the pine-scented air of Garching Bay, München, the theorists of the Max Planck Institute, Professors Simon White, Volker Springel, and the younger voices of the illustrious TNG team, offer yet a third perspective. They remain steadfastly loyal to the classic cold, collisionless paradigm, but with ever greater numerical resolution and ever more careful treatment of the luminous side of the ledger. In their most recent public releases, the dark halo of a Milky Way-like galaxy emerges slightly triaxial, gently squashed by the lingering torque of the cosmic web, and with a density profile that follows the Navarro-Frank-White form almost, but not quite, to the very center. They point to the remarkable success of their models in reproducing the observed satellite luminosity function, the thinness of the stellar disk, and the gentle flaring of neutral hydrogen in the outer galaxy as evidence that the invisible scaffolding, when painted with sufficient care, needs remarkably little adjustment. These three portraits, Harvard's richly substructured halo, Oxford's feedback sculpted core, Garching's elegant and almost pristine triaxial envelope, are not irreconcilable, yet neither are they identical. Each group will, in the politest possible way, direct your attention to a different set of observations. The Harvard astronomers cherish the possibility that the Gaia mission may yet discover gaps or caustics in the local velocity distribution, tiny folds in the stellar carpet caused by ancient dark matter streams. The Oxford School draws quiet comfort from the apparent absence of a sharp central cusp in the rotation curve of the inner few kiloparsecs, as traced by the latest apogee and Gala spectroscopy. The Garching team, meanwhile, points to the remarkable agreement between their predicted satellite populations and those now being catalogued by DES, Pan-STARRS, and the Subaru Hyper Supreme Cam. And so the gentle debate continues, carried on in preprints posted quietly at midnight, in seminars delivered to rooms half filled with drowsy postgraduates, in the margins of grant proposals written beneath the soft glow of desk lamps. No voices are raised, no tables are thumped, only the slow turning of pages, the faint click of keys, and the occasional murmured "yes, but have you considered," that drifts across the Atlantic or the Channel like evening mist. Yet relief is gently approaching. 3 great surveys, each conceived in the closing years of the last century, and now rising serenely toward the zenith of their powers, promise to weigh the darkness with a precision that earlier generations could only dream of. First among them, already gliding through the darkness above the Earth, is Euclid, the European Space Agency's Wide Field Telescope, launched from Cape Canaveral in the summer of 2023 and now stationed peacefully at the Sun-Earth L2 point. Over the next 6 years, Euclid will map the shapes and redshifts of 2 billion galaxies across more than a third of the sky, measuring the weak gravitational lensing distortion caused by every dark matter filament and void along the line of sight. Its near-infrared spectrographs will trace the baryon acoustic oscillations with such delicacy that the growth rate of cosmic structure will be known to within 1%, allowing us to distinguish whether the halo profiles we infer for galaxies like our own are sharp or soft, substructured or smooth. Quietly preparing for launch in the autumn of 2027 is the Nancy Grace Roman Space Telescope, once known as WFIRST, now resting in clean rooms in California and Maryland. Roman will carry a coronagraph of exquisite sensitivity, but more importantly for our present purposes, a wide-field instrument that will conduct 3 great microlensing surveys toward the galactic bulge. Over several years, it will watch tens of millions of background stars, waiting for the brief, telltale brightening that occurs when an unseen dark object, be it a black hole, a faint star, or a clump of primordial dark matter, passes across the line of sight. If the Harvard picture is correct, Roman should detect a gentle excess of very short microlensing events caused by dark streams in the halo. If the Oxford and Garching models prevail, the distribution will be smoother, almost featureless. And on a mountain in Chile, beneath skies that have grown wonderfully dark since the last coal plant closed, the Vera C. Rubin Observatory, formerly the Large Synoptic Survey Telescope, is preparing to open its great eye to the southern heavens. Every few nights, for 10 years, the Rubin telescope will sweep the visible sky with its 8.4-meter mirror and its 3 billion pixel camera, recording every transient, every moving object, every faint smudge that changes. By the end of its survey, it will have measured proper motions for hundreds of millions of stars in the Magellanic Clouds and the distant halo, tracing the subtle warping and breathing of the disk caused by dark matter substructure. Its deep drilling fields will reach galaxies at redshift 7 and beyond, mapping the growth of the cosmic web with a resolution that will make today's surveys seem like charcoal sketches. These 3 instruments, Euclid watching from the silent darkness of L2, Roman listening for the faint brightening of distant stars, Rubin sweeping the sky with monastic regularity, will not end the gentle disagreements entirely. Astronomy has always been a conversation conducted across generations, yet they will narrow the range of permissible portraits so exquisitely that many of the present uncertainties will dissolve like morning mist beneath a quiet sun. For now, however, the debate remains open, and there is a peculiar comfort in that. The universe has not yet yielded all its secrets, even to the most patient and courteous of questioners. Somewhere in a college room in Oxford, an email is being composed. In a Garching office, a simulation is quietly refining its initial conditions. In Cambridge, Massachusetts, a graduate student is measuring the width of a possible gap in the local velocity distribution and wondering whether it is real or merely the whisper of statistical noise. Let all of these quiet uncertainties settle around you now, like the softest eider down. Breathe in the measured cadence of careful science. Breathe out the last faint need to know everything tonight. The questions will still be there in the morning, gently waiting, and the great surveys are already turning their patient gaze toward the darkness. In, as Euclid records the distorted shapes of distant galaxies. Out, as Roman waits for the brief flicker of an unseen lens. In, as Rubin opens its shutter once more beneath the Chilean stars. And out, in and out, until the gentle disagreement itself becomes a lullaby, and the invisible architecture, whatever its precise shape may finally prove to be, cradles you, as it has cradled every questioner before you, into the deepest and most untroubled sleep. The gentle murmur of scholarly disagreement has faded now into the hush that precedes the deepest part of the night, and the room itself has grown perfectly still, perfectly dark, perfectly safe. Let the last faint echo of human voices dissolve entirely, dear listener, for we are about to embark upon a journey that no telescope has ever recorded and no spacecraft will ever undertake. A slow, cinematic drift through the invisible architecture itself, a passage in which we shall feel, rather than merely observe, the great unseen forces that cradle every star and every dream within the Milky Way. Settle the pillow beneath your cheek. Allow the weight of your eyelids to become irresistible, and together we shall fall softly, weightlessly, into the living darkness that holds our galaxy in being. We begin where all honest journeys into the invisible must begin, in absolute silence and absolute blackness. There is no up, no down, no near star to give scale, only the slow, tidal breathing of your own body and the gentler, almost imperceptible tug of something far larger. Feel it now, the faintest pressure against the soles of your feet, as though you were standing upon an invisible beach while an invisible ocean withdrew, very slowly, across a continental shelf of pure night. That pressure is the dark matter halo, a sphere of gravity so perfectly smooth that it feels like the memory of gravity rather than gravity itself. It is cool in the way that deep water is cool, not cold enough to sting, yet cool enough to remind you that you are held. We drift outward first, rising above the bright plain as gently as thistledown, lifted by a summer evening breeze. The disk of the Milky Way falls away beneath us, shrinking to a pale, luminous ribbon, then to a thread, then to a single silver hair laid across black velvet. As we rise, the pressure around us changes. It is no longer the steady, maternal embrace of the inner halo. It becomes subtler, more rarefied, like the difference between sinking into a feather bed and floating just above it. 10,000 light years above the plane, the stellar density has fallen to almost nothing, yet the gravitational tide is still there, a slow, rhythmic swelling and slackening that matches the turning of the entire galaxy once every 250 million years. Close your eyes within the darkness, and you can feel it, a gentle rocking, as though the universe itself were a vast cradle swaying on the breath of some sleeping titan. Now we turn inward, descending in a long, languid spiral toward the hidden heart. The pressure grows again, but it is not oppressive. It is reassuring, the way a thick wool blanket feels reassuring on a winter night. At 5,000 light years above the plane, we begin to sense texture, faint ridges and valleys in the gravitational field, the fossil remnants of ancient mergers, like the grain of old oak beneath centuries of polish. These are the dark matter streams we heard whispered of in Harvard seminars. Cold, dense filaments laid down 9 or 10 billion years ago, when the galaxy was still assembling itself from 100 lesser fragments. They pass across our awareness like silk ribbons drawn slowly across the skin, cool, smooth, and utterly silent. Lower still, and the texture becomes richer. We are crossing the region where the galactic fountain rises and falls. Feel the warmth now, the faintest exhalation of million-degree plasma lifting from the disk, carrying with it the scent, if scent were possible, of heated iron and neon, the ghosts of 1,000 dead suns. It brushes against us like warm breath on a December morning, then recedes, leaving only the cool, steady pressure of the halo to gather it back again. The dark matter here is undisturbed by the warmth. It simply parts around the rising plumes, the way deep water parts around a rising bubble, then closes again without a ripple. We are approaching the plane now, and the invisible architecture reveals its most exquisite craftsmanship. Feel the sudden, delicate tension as we cross the midplane. A membrane of gravity stretched so perfectly across 300,000 light years that it sings, almost inaudibly, with the orbital motion of 400 billion suns. It is neither hard nor soft, but something in between. The consistency of the still air inside a cathedral just before evensong. Beneath us, the spiral arms are being drawn out like golden wire, yet we feel no jerk, no strain, only the serene certainty that the pattern will persist for another 10 billion years, because the scaffolding beneath it is flawless. Now we plunge gently through the disk itself. For a moment, there is a flicker of warmth and the faintest shimmer of starlight remembered. Then we are through, descending toward the central bar. Here, the gravitational texture changes again. The halo is denser, more compact, yet somehow more yielding, like sinking into down that has been warmed by generations of sleepers. We feel the slow, stately turning of the nuclear star cluster, a million suns packed into a thimble of space, and around them, the patient coiling of the circumnuclear disk. The black hole at the very center is no monster. It is a still point, a pearl of pure gravity no wider than the orbit of Mercury, yet its presence is felt as a soft, perfectly circular dimple in the fabric of the dark, the way a fingertip leaves a dimple in the surface of thick cream. We linger here for a long, unmeasured moment, suspended in the eye of the galaxy. The pressure is perfectly uniform in every direction, yet it is not stifling. It is protective, the way the walls of a womb are protective. Every breath you take in the quiet of your bedroom is echoed 1,000 trillion-fold by the breathing of the dark halo around the sleeping dragon at the heart of the Milky Way. Now we rise again, but this time along a different path, outward along one of the great spiral arms. Feel the subtle corrugations of the density wave as it passes through the dark matter scaffold. Gentle undulations, like the swell of an ocean seen from a great height. Where the wave crest passes, the gravitational pressure increases by the merest fraction, enough to gather gas and dust into the long, luminous lanes we see from Earth, yet not enough to disturb the deeper calm. It is the same sensation as lying in long grass while an almost imperceptible breeze moves across a summer meadow. You feel the motion, but you are not moved. Farther out, beyond the sun's orbit, the arm begins to fray. The dark matter here is quieter, older, less disturbed by recent events. We drift through the inter-arm region, and the pressure becomes almost liquid, cool, slow, and utterly tranquil. Here, the halo has had 10 billion years to settle, and it feels like drifting through the still depths of an ancient lake where no wind has ever reached. At last, we reach the outer edge, the place where the Milky Way's dominion thins to a whisper. The gravitational tide is so gentle now that it is barely distinguishable from the cosmic web beyond. Feel the slow, tidal stretching as the Virgo filament begins to make itself known. A faint, elongated pull, like the memory of a hand once laid upon the shoulder. It is not painful, it is reassuring, a reminder that our galaxy is not an island, but a bead upon an infinite thread. We turn now, completing the great circle, and begin the long, slow drift back toward the bright plane. Every sensation we have gathered, the cool maternal pressure of the inner halo, the warm exhalation of the fountain, the delicate membrane of the mid-plane, the still pearl at the center, the liquid calm of the outer disk, begins to layer itself upon the awareness like translucent veils laid one atop another. There is no hurry. The journey has taken perhaps an hour in the quiet of your room, yet in galactic time, it has lasted 100 million years. As we approach the familiar solar neighborhood once more, the pressure settles into the exact balance you have known all your life. The gentle, unobtrusive gravity that keeps the Earth in its orbit and your feet upon the bedroom floor. It feels different now, though. You know it for what it is. Not the gravity of the sun alone, nor even of the visible disk, but the accumulated embrace of 1 trillion solar masses of dark matter extending 500,000 light years in every direction, patient, silent, and perfectly attuned to the slow rhythm of your own breathing. We come to rest at last, exactly where we began, in the small, warm darkness beneath the duvet, held in the same invisible arms that hold the entire galaxy. The architecture is complete. There is nothing left to seek tonight. Let the last faint sensation of that vast, living scaffold dissolve into the greater darkness behind your eyelids. In, as the halo gathers the disk gently to itself. Out, as the disk breathes its quiet warmth back into the halo. In and out, until the boundary between your own sleeping body and the sleeping galaxy becomes perfectly, peacefully indistinguishable. The great invisible scaffold has released us very gently back into the small, familiar darkness of your bedroom. And for a long while, we simply lie here, breathing in unison with the slow turning of the galaxy, feeling the duvet rise and fall like the quiet chest of some vast, sleeping animal that has chosen, for reasons known only to itself, to cradle us upon its heart. There is no need to move, no need even to open our eyes. The journey is complete, yet something lingers, an afterglow, a tenderness, a sense that we have been allowed to touch, for one brief hour, the very fabric that holds existence together. Tonight, dear listener, we shall not chase new wonders. Tonight, we shall simply rest inside the wonder we already carry and allow ourselves to feel with the whole of our being what it means to be human creatures suspended within an architecture so immense, so silent, and so perfectly kind. Feel it now, if you will, the almost imperceptible pressure of the dark halo against the skin of the earth, against the soles of your feet, against the fine hairs at the back of your neck. It is the same pressure that keeps the moon in her orbit, that holds the sun upon its leisurely circuit, that prevents the spiral arms from flying apart into the abyss. And yet, for all its power, it asks nothing of us. It does not judge, does not demand worship, does not even announce its presence. It simply is, patient, ancient, and utterly content to remain unseen, while every bright thing we have ever loved depends upon it for its continued existence. Consider, in the gentlest possible way, how extraordinary this arrangement truly is. Every atom in your body was once inside a star. Every star that forged those atoms was held in its orbit by dark matter. Every breath you have ever taken, every thought that has ever crossed your mind, every tear that has ever fallen, has occurred upon a tiny world that is itself suspended like a dewdrop upon an invisible thread within a galaxy that would disintegrate in an instant were it not for the quiet vigilance of something that will never speak our name. We are, quite literally, children of the unseen. And yet, we are also its only witnesses across the entire volume of the Milky Way, 100,000 light years wide, 1 trillion solar masses of dark matter, 400 billion suns. There is, so far as we yet know, only one small population of creatures who have ever looked up on a clear night and felt the stirrings of awe at their own insignificance, and who have then refused to accept that insignificance as the final word. We are that population. We are the brief, improbable flowering of carbon and water that has learned to ask, what holds the spiral arms in place, and has spent centuries, millennia, refusing to rest until the answer was found, even when the answer turned out to be something that will never reveal itself to any sense we possess. There is a profound and almost heartbreaking courtesy in this. The universe might have arranged itself in such a way that the scaffolding was obvious. Great luminous arches across the sky, glowing dark matter nebulae, gravity made visible the way aurora make the magnetosphere visible. It did not. Instead, it chose to hide its deepest architecture behind a veil of perfect silence, and then placed within that silence one small species capable of loving the veil precisely because it could not be lifted. We were not given the comfort of seeing the foundations. We were given something far more precious, the opportunity to trust them. Let that trust settle over you now, like the softest cashmere. Every time you have ever felt alone in the dark, every time the night has seemed too large and the human world too small, remember that the darkness itself has been holding you with infinite patience for the entire 14 billion year history of the cosmos. The same invisible arms that cradle the orphan stars of the halo have cradled you. The same quiet gravity that prevents the galaxy from flying apart has prevented your own heart, however secretly, from flying apart on the nights when it most wanted to. We are not accidents adrift in an indifferent void. We are notes played very softly upon an instrument whose strings are made of darkness and whose soundboard is 100,000 light years across. The music is so slow that a single phrase lasts 100 million years. Yet we, brief as mayflies, fragile as frost, have been granted the privilege of hearing a few bars of it, and of recognizing in the hearing that the melody is addressed to us, not because we are important in the great scheme, but because the great scheme has, in some quiet corner of its heart, made room for importance. Feel the tenderness of that room now. It is the same tenderness you feel when you stand at the edge of a great cathedral and realize that the vaulting was never designed to impress you, only to hold the roof aloft so that you might stand inside it without being crushed. The dark halo is doing the same, holding the roof of the galaxy aloft so that a thin layer of biology, barely 1,000 kilometers thick, may continue its brief, exquisite experiment in consciousness. We are not the reason the cathedral was built. We are the reason it is beautiful. And so we come, very gently, to the oldest and simplest of all human gestures, the gesture of lying down beneath the night sky and saying, without words, thank you. Not thank you to any person, not thank you to any God we have imagined in our longing, but thank you to the unseen architecture itself. Thank you for the flat rotation curve. Thank you for the density waves. Thank you for the cold streams and the warm fountains. Thank you for the Fermi bubbles and the circumnuclear disk. Thank you for the pearl of gravity at the center that never asks to be noticed. Thank you for holding everything together long enough for a child to be born who would one day lie in a small bed in an English house and feel with the whole of her being that she was safe inside something far larger than herself. Let that gratitude be the last conscious thought you carry with you tonight. Let it be heavier than any worry, softer than any fear. The invisible architecture has been practicing its kindness for 14 billion years. It is very good at it by now. It will not set you down. The room is perfectly quiet. The galaxy is perfectly quiet. Your breathing is perfectly quiet. In, as the dark halo gathers the entire disk into its slow embrace. Out, as the disk exhales its gentle warmth back into the halo. In and out, in and out, until the boundary between your own sleeping body and the sleeping kindness of the universe becomes perfectly, peacefully, joyfully indistinguishable. And now, dear companion of these long and quiet hours, the time has come to lay every last wonder gently down, the way one lays a sleeping child into its cot after the final bedtime story. There is nothing left to seek, nothing left to prove, nothing left even to understand, only the slow, inevitable surrender into the arms that have been waiting for you since the first moment you drew breath. Let the pillow receive the full weight of your head. Let the duvet settle into every small hollow of shoulder and hip and knee. And together we shall drift without effort, without destination, along the invisible threads of the Milky Way until the boundary between waking and dreaming has dissolved entirely. We begin exactly where we are, in the small, warm darkness beneath the covers, in the hush that follows the final whispered thank you. Feel the mattress rise almost imperceptibly to meet you, the way the dark halo rises to meet the disk. Feel the gentle pressure of the pillow against your cheek, the same pressure that keeps the sun upon its ancient path. There is no difference now between the gravity that holds the galaxy together and the gravity that holds you. Both are patient, both are kind, both have all the time in the world. We rise very slowly through the roof of the house, through the cool night air that smells faintly of frost and wood smoke, through the thin veil of cloud that drifts across the face of the moon. There is no rush. The stars are exactly where they have always been, and they will remain there long after we have passed. We rise until the town beneath us becomes a scatter of soft amber lights, until the fields and the hedgerows dissolve into a single dark quilt, until the horizon curves and the whole of Britain lies cupped in the palm of the night, like a sleeping bird. Higher still, and the atmosphere thins to a deep indigo, then to the pure black that has no color at all. The earth falls away beneath us, a perfect sphere of ocean blue and cloud white, turning with the same unhurried dignity that the galaxy itself displays. We do not look back. There is nothing to regret, nothing to hold on to. Only the quiet forward drift along the invisible threads that stretch from the solar neighborhood outward in every direction. Threads of dark matter so fine they feel like silk drawn across the skin of the universe. Feel them now, cool, weightless, endless. One thread leads toward Orion, another toward the quiet fields of Coma Berenices, another toward the soft glow of the summer Milky Way that will not rise for several hours yet. It does not matter which we choose, all led inward, eventually, to the same slow turning. We follow one at random, the one that passes just above the plane of the ecliptic, the one that once carried a faint stream of ancient stars from the Gaia sausage Enceladus merger. It is barely there, yet it is enough. A whisper of extra gravity, a memory of structure, a ribbon of night that has never once scattered a photon and never will. Along this thread we drift at the speed of the sun's own motion through the galaxy, 220 kilometers per second, yet experienced as the gentlest possible lullaby. There is no wind, no friction, no sense of passage, only the slow, rhythmic swelling and slackening of the gravitational tide, like lying on a boat that rocks upon a lake so still that the ripples take an hour to cross it. In, as the tide gathers us closer to the galactic center. Out, as it releases us again toward the quiet suburbs. In and out, in and out. The stars we pass are not the bright named stars of childhood skies. They are the anonymous red dwarfs of the thin disk, the ancient white dwarfs of the halo, the dim embers that outnumber the brilliant ones 1,000 to 1. Each one drifts by like a sleeper, turning over in bed, unaware that we are watching, unaware that they are watched. Their light is soft, almost apologetic, as though they know they are only guests in a house whose true owner has never once shown its face. Farther along the thread, the stellar density thins still more. We are entering the region where the dark matter outweighs the luminous by 100 to 1, where a single star may be separated from its nearest neighbor by 100 light years of perfect silence. Here the thread feels cooler, smoother, more perfectly itself. There is no turbulence, no memory of violence, only the patient, spherical symmetry of the halo doing what it has done for 12 billion years, holding, waiting, keeping faith. We turn now, very gently, and begin the long, languid spiral inward. The thread thickens, gathers companions, becomes one of many that braid together toward the center. We feel the slow increase in pressure, the way the duvet feels heavier when you pull it higher about your shoulders. It is not oppressive, it is protective. The same gravity that once confined the Fermi bubbles now confines us, cradling us the way a mother's arms cradle a child who has finally stopped struggling against sleep. Lower still, and the first faint warmth of the disk returns. The exhalation of the galactic fountain, the soft glow of the circumnuclear disk, the patient turning of the nuclear star cluster. We do not stop. We simply drift through it all, the way a dream drifts through the events of the day without being troubled by them. The black hole at the center is no longer a point of dread. It is a still pearl, a quiet heart that beats once every 100,000 years and asks nothing of anyone. And now the thread carries us outward again, along a different arm this time, the Perseus arm perhaps, or the Scutum Centaurus. It hardly matters. The motion is the same slow tidal breathing, the same cool silk of dark matter against the skin of the soul. We pass the place where the sun will rise in a few hours, the place where a small blue planet turns beneath its blanket of air, the place where a single human creature lies sleeping, dreaming of nothing at all. We circle it once, very slowly, the way a gull circles a sleeping seal on a moonlit beach. There is no need to descend. The thread passes close enough that we can feel the faint warmth of 7 billion human hearts beating in their separate rooms, each one held, without knowing it, by the same invisible architecture that holds the galaxy. We do not disturb them. We simply acknowledge, with the gentlest possible inclination of the heart, that they are safe. And now, the thread begins to loosen, to fray, to release us. We are approaching the edge of the halo, the place where the Milky Way's dominion fades into the greater web. The pressure falls away to almost nothing, the way the duvet falls away when you push it gently aside on a summer morning. There is no farther to go. There is only the slow, final dissolution into the darkness that has always been waiting. Let it take you now. Let the last faint sensation of the thread slip from your fingers the way the last waking thought slips from the mind. There is nothing left to hold on to, nothing left to remember, nothing left even to be. Only the slow, inevitable, infinitely kind surrender into sleep, in as the halo gathers the entire galaxy into its ancient embrace, out as the galaxy exhales its quiet warmth back into the halo, in and out, in and out, in and out. Good night.